March 21, 1942, Willow Run, Michigan. Henry Ford II stands in a cavernous factory space that stretches beyond the horizon, watching as the final rivets are driven into the nose section of a B-24 Liberator bomber. The aircraft gleams under harsh industrial lighting, its aluminum skin reflecting the organized chaos of the world's most ambitious manufacturing experiment. Ford checks his stopwatch and makes a notation on his clipboard. 63 minutes, another bomber complete. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What he's witnessing shouldn't be possible, according to every aviation expert in America. Heavy bombers aren't automobiles. They can't be mass-produced on assembly lines like Model T Fords. Each aircraft contains over 1.5 million individual parts, requires precision tolerances measured in thousandths of an inch, and demands skills that take years to develop. Yet here at Willow Run, civilian workers with no aviation experience are turning out 4-engine bombers faster than some factories produce cars. The military contractors who built aircraft the traditional way are calling it impossible, illegal, and dangerous. Consolidated Aircraft, the company that originally designed the B-24, insists that proper bomber construction requires master craftsmen, custom tooling, and careful hand-fitting of components. They're producing perhaps one B-24 per day at their San Diego facility, using methods unchanged since the Wright brothers. Ford Motor Company is about to prove them catastrophically wrong. But this revolution in aircraft manufacturing didn't begin with patriotic fervor or military contracts. It started with one man's obsession with efficiency and his absolute conviction that any manufacturing problem could be solved by applying automotive production principles on an unprecedented scale. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story begins not with Pearl Harbor, but with a meeting that took place 6 months before America entered the war. September 1941, Washington, D.C. Charles Sorensen, Ford Motor Company's chief of production, sits across from Army Air Force's procurement officers who are desperately seeking ways to increase bomber production. The British are screaming for more aircraft. The Soviet Union, barely holding on against German advances, needs American-built planes immediately. Current production rates are pathetic. All American aircraft manufacturers combined are producing fewer than 100 bombers per month. At this rate, it would take decades to build the air armadas that military planners envision. Sorensen listens to the specifications for the consolidated B-24 Liberator and makes calculations in his head. Wingspan, 110 feet. Length, 67 feet. Empty weight, 36,000 pounds. Maximum takeoff weight, 65,000 pounds. To traditional aircraft manufacturers, these numbers represent months of careful assembly work. To Sorensen, they represent a manufacturing challenge that automotive methods could solve. He's already revolutionized automobile production by breaking complex assembly processes into simple, repetitive tasks that semi-skilled workers could master quickly. Why couldn't the same principles apply to bombers? The military officials are skeptical. Aircraft manufacturing isn't automobile manufacturing. Bombers require precision that mass production can't achieve. Each component must be individually fitted, tested, and adjusted. Quality control demands highly trained specialists who understand aerodynamics, structural engineering, and precision metalwork. You can't just hire factory workers off the street and expect them to build aircraft that won't fall apart at 25,000 feet. Sorensen disagrees fundamentally. He's spent 20 years proving that complex manufacturing problems yield to systematic analysis and standardized processes. The secret isn't skilled craftsmen working individually. The secret is breaking every job down to its essential elements, creating foolproof procedures, and organizing workflow so that each worker performs one specific task perfectly, repeatedly, without requiring deep technical knowledge. But there's a problem that goes beyond manufacturing philosophy. The B-24 Liberator is owned by Consolidated Aircraft Corporation. Reuben Fleet, Consolidated's founder and president, has built his company's reputation on quality craftsmanship and traditional aviation methods. His engineers and workers have spent years perfecting the B-24 design. His factory in San Diego represents everything the aviation industry believes about proper aircraft construction. Fleet has no intention of sharing his design with Ford Motor Company, whom he considers automotive upstarts with no understanding of aviation requirements. The B-24's blueprints, tooling specifications, and manufacturing processes are proprietary information that Consolidated has invested millions to develop. Why should they hand over their competitive advantage to a car company? The deadlock might have continued indefinitely, but Pearl Harbor changed everything. December 7, 1941, transforms American manufacturing priorities overnight. Suddenly, academic debates about production philosophy become matters of national survival. President Roosevelt demands that American factories produce 60,000 aircraft in 1942, including thousands of heavy bombers. Consolidated's San Diego facility, working at maximum capacity with traditional methods, might produce perhaps 365 B-24 seconds per year. The Army Air Forces needs thousands. There's only one company in America with the manufacturing capacity, engineering expertise, and production experience to attempt mass production of heavy bombers: Ford Motor Company. Reuben Fleet capitulates reluctantly in early 1942, under enormous government pressure and facing the reality of wartime production demands. Consolidated agrees to share B-24 specifications with Ford. But Fleet makes his skepticism clear. Ford can try their assembly line methods, but when their experiment fails, Consolidated will be ready to resume proper bomber production using proven techniques. Charles Sorensen arrives at Consolidated's San Diego facility in February 1942 with a team of Ford engineers who begin what amounts to industrial espionage. They measure everything, photograph every process, document every tool and technique. Traditional aircraft workers watch these automotive engineers with mixture of amusement and disdain. These car builders have no idea what they're getting into. Aircraft manufacturing isn't just complicated. It's an art form that requires intuition, experience, and craftsmanship that can't be reduced to simple procedures. A master riveter knows by feel when a joint is properly seated. An experienced assembler can spot misaligned components by eye. Quality control specialists understand structural engineering principles that take years to learn. You can't replace that knowledge with assembly line procedures. Sorensen sees something entirely different. He watches Consolidated workers custom-fitting each component, hand-adjusting connections, individually testing systems. What aircraft manufacturers call precision, he calls waste. Every custom adjustment represents a design flaw that proper engineering could eliminate. Every hand-fitting operation represents a process that standardization could streamline. Most significantly, he observes that Consolidated builds each B-24 as a unique project. Workers gather materials, components, and tools around each aircraft, then spend weeks assembling that specific bomber from start to finish. It's the same method medieval craftsmen used to build carriages, scaled up but fundamentally unchanged. Sorensen envisions something revolutionary. A continuously moving assembly line where B-24 components flow through specialized stations, with workers performing identical operations on every aircraft. Instead of building bombers individually, Ford would manufacture them systematically, with each worker becoming expert at one specific task, rather than trying to master the entire aircraft. The concept faces immediate technical obstacles. Automobiles weigh 3,000 pounds and contain perhaps 10,000 parts. B-24 bombers weigh 36,000 pounds empty and contain over 1.5 million individual components. The physical challenges of moving such massive aircraft through an assembly line seem insurmountable. Traditional aircraft assembly keeps each bomber stationary, while workers bring tools and materials to the aircraft. Sorensen proposes the opposite. Keep the workers stationary while the aircraft moves past them. But moving a 67-foot-long bomber with 110-foot wingspan through a factory requires engineering solutions that don't exist. The wingspan problem seems particularly intractable. 110 feet exceeds the width of most factory buildings. How do you move an aircraft with extended wings through a standard manufacturing facility? Consolidated solves this by assembling wings separately, then mating them to fuselages in a final assembly area. But this requires enormous amounts of factory space and complicates the assembly sequence. Sorensen's team develops an ingenious solution. Assemble the fuselage and wings separately on parallel assembly lines, then mate them together as the final step. This allows the factory to be narrower while maintaining continuous workflow. Wings move down one line while fuselages progress down another, converging only at the end. But even this approach requires a factory of unprecedented size. Sorensen calculates that efficient B-24 production needs a building at least 3,000 feet long and 1,200 feet wide. This would be the largest manufacturing facility ever constructed, covering more ground than many small towns. Henry Ford approves the concept immediately. If America needs bombers, Ford Motor Company will build the biggest factory in history to produce them. Groundbreaking for the Willow Run facility begins in April 1942, while Sorensen's team continues studying B-24 manufacturing requirements. The facility's scale defies comprehension. 3,300 feet long, 1,200 feet wide, covering over 67 acres under one roof. The main assembly building alone contains more floor space than the Pentagon. Railroad tracks run directly through the factory so that materials can be delivered to specific assembly stations. The facility includes its own power plant, water treatment facility, and fire department. Construction proceeds 24 hours per day, using techniques borrowed from automotive factory construction but scaled up dramatically. Steel framework rises in sections, while concrete pours continuously. The building progresses from foundation to partial operation in less than 6 months, a construction pace that breaks every existing record for industrial building. But the real revolution isn't architectural, it's methodological. Sorensen's team spends months breaking down B-24 assembly into discrete operations that can be performed by workers with minimal training. Every rivet, every bolt, every wire connection becomes a standardized procedure with specific tools, exact specifications, and foolproof quality control measures. Traditional aircraft workers require years of training to become competent. Sorensen designs assembly processes that new workers can master in weeks. Instead of requiring workers to understand the entire aircraft, each person learns one specific operation perfectly. A worker who installs control cables doesn't need to understand hydraulic systems. A riveter doesn't need to comprehend electrical circuits. This specialization horrifies aircraft industry traditionalists. How can workers who don't understand aircraft engineering possibly build reliable bombers? What happens when problems arise that require technical knowledge and creative problem solving? Assembly line workers can't troubleshoot complex issues or adapt to unexpected circumstances. Sorensen's answer is systematic quality control built into every step of the process. Instead of relying on worker expertise to catch problems, Ford designs the manufacturing process to prevent problems from occurring. Every component is precisely measured before installation. Every connection is tested immediately after completion. Every system is verified before the aircraft proceeds to the next station. Quality becomes a function of process control rather than individual expertise. Workers don't need to be experts because the procedures they follow are designed by experts and validated through extensive testing. If everyone follows the specified process exactly, the result will be a properly assembled bomber, regardless of individual worker knowledge or experience. The first B-24 seconds begin moving down the Willow Run assembly line in September 1942, 6 months after construction began. The early aircraft require significant hand finishing and adjustment, but they're recognizably Liberator bombers built to the same specifications as Consolidated's handcrafted aircraft. More importantly, they're being produced much faster than traditional methods allow. Where Consolidated requires weeks to complete a bomber, Willow Run is completing aircraft in days. The assembly line moves continuously, with new bombers emerging at regular intervals rather than sporadically as individual projects finish. Critics point out quality problems with early Willow Run aircraft. Panels don't fit perfectly. Some systems require adjustment after assembly. Finish quality doesn't match hand-built aircraft standards. But Ford engineers are systematically identifying and correcting each problem through process improvements rather than increased worker skill. Every defect becomes a learning opportunity. If panels don't fit properly, the stamping dies are adjusted. If systems need post-assembly adjustment, the installation procedures are refined. If finish quality is poor, surface preparation processes are improved. The assembly line becomes self-correcting, with each problem generating solutions that prevent recurrence. By early 1943, Willow Run is producing B-24 seconds that meet all military specifications while requiring minimal post-assembly work. More significantly, production rates are accelerating as workers master their specific tasks and process improvements eliminate bottlenecks. The transformation is remarkable. Workers who had never seen an aircraft 6 months earlier are now building bombers that pass rigorous military inspections. Assembly line principles that revolutionized automobile manufacturing are proving equally effective for aircraft production, despite universal predictions that such methods would fail catastrophically. But the real breakthrough comes in March 1943, when Willow Run achieves something unprecedented in aviation history: continuous flow production of heavy bombers. Instead of building aircraft in batches or individual projects, Ford is manufacturing B-24 seconds as a continuous stream, with completed bombers emerging from the assembly line at regular, predictable intervals. The psychological impact on both workers and observers is profound. Aircraft manufacturing has always been viewed as a craft requiring exceptional skill and lengthy timeframes. Suddenly, bombers are being produced with the same systematic efficiency as automobiles. What seemed impossible 12 months earlier has become routine daily operation. Military procurement officers who initially doubted Ford's capabilities are now scrambling to place additional orders. The bottleneck in bomber production has shifted from manufacturing capacity to raw materials and component supply. Willow Run can build bombers faster than suppliers can provide engines, propellers, and specialized equipment. Reuben Fleet and Consolidated Aircraft face an uncomfortable reality. Their traditional manufacturing methods, which they believed represented the pinnacle of aviation engineering, are being surpassed by automotive techniques applied to aircraft production. Ford Motor Company, with no previous aviation experience, is outproducing Consolidated by factors that seem impossible. The implications extend far beyond B-24 production. If heavy bombers can be mass-produced using assembly line methods, what other impossible manufacturing challenges might yield to systematic analysis and automotive techniques? The war is revealing that American industrial capacity, properly organized and efficiently managed, can achieve production levels that no other nation can match or counter. By late 1943, Willow Run has achieved something that defies every prediction made by aviation experts 18 months earlier. The facility is producing one B-24 Liberator every hour and 7 minutes, a rate that exceeds the combined output of all other American bomber factories. But Henry Ford isn't satisfied. One bomber per hour still represents inefficiency in his mind, wasted motion and unnecessary delays that proper engineering could eliminate. Ford walks the assembly line personally, stopwatch in hand, observing every operation with the same intensity he once applied to Model T production. He sees workers waiting for parts, tools that require extra steps to retrieve, materials positioned inefficiently around workstations. Each delay, however small, compounds across the entire production process. The mathematics are brutal but revealing. If workers waste 30 seconds per station, and there are 80 stations in the assembly sequence, that's 40 minutes of accumulated delay per aircraft. 40 minutes represents 2/3 of a bomber that could be produced if workflow were optimized perfectly. Ford demands that his engineers eliminate every second of wasted time. The challenge isn't just mechanical, it's human. Assembly line work requires precise timing and coordination between hundreds of workers performing interdependent tasks. A delay at any station backs up the entire line. A mistake at one position creates problems that cascade through subsequent operations. Traditional manufacturing tolerates such irregularities by building buffers and allowing time for corrections. Ford's approach eliminates buffers entirely. Every component must arrive at exactly the right moment. Every worker must complete their assigned tasks within precisely allocated time. Every tool must be positioned for maximum efficiency. The assembly line becomes a precision instrument where human workers function as interchangeable components in a carefully orchestrated mechanical process. This philosophy horrifies labor advocates and traditional craftsmen who view such systematization as dehumanizing. Workers become cogs in an industrial machine, stripped of individual creativity and reduced to repetitive motions. The assembly line demands conformity, consistency, and subordination to mechanical rhythms that ignore human preferences or natural working patterns. But the results are undeniable. By January 1944, Willow Run achieves production rates that approach Ford's theoretical targets. Bombers emerge from the assembly line every 68 minutes. Each aircraft contains exactly the same components installed using identical procedures by workers who have mastered their specific tasks through constant repetition. Quality. Metrics tell a remarkable story. Willow Run B-24s require fewer post-assembly corrections than hand-built aircraft from traditional manufacturers. Standardized procedures eliminate the human errors that custom fabrication introduces. When every worker follows identical processes using precisely specified tools, variations that cause problems simply don't occur. Military inspectors who initially doubted mass-produced aircraft quality now prefer Willow Run bombers over traditionally manufactured alternatives. The systematic assembly process creates uniformity that individual craftsmanship can't match. Parts are interchangeable between aircraft. Maintenance procedures are standardized. Pilots report that Willow Run B-24s handle more predictably than hand-built variants. The transformation of the workforce reveals something profound about human adaptability under industrial conditions. Workers who arrived at Willow Run with no aviation experience have become specialized experts at their specific assembly tasks. A riveter who installs wing panels can work faster and more accurately than traditionally trained aircraft assemblers who attempt to master multiple skills. Specialization creates expertise that generalization cannot achieve. Workers who perform identical operations thousands of times develop unconscious competence that surpasses conscious knowledge. Their hands know proper technique without requiring mental attention. They detect problems through tactile feedback that formal training couldn't provide. Charles Sorensen documents this phenomenon in production reports that read like studies in industrial psychology. Workers initially resist assembly line methods, preferring variety and autonomy that traditional craftsmanship provides. But within weeks, they adapt to systematic procedures and begin suggesting improvements that engineers hadn't considered. The suggestions aren't random. They reflect intimate knowledge of specific operations that only constant repetition can provide. A worker who installs control cables 8 hours daily notices inefficiencies that design engineers missed. Someone who operates the same machinery continuously identifies optimization opportunities that occasional users never discover. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Ford implements these worker suggestions systematically, testing each proposed change and incorporating successful modifications into standard procedures. The assembly line becomes self-improving, with frontline workers contributing to continuous optimization that keeps accelerating production rates. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By March 1944, Willow Run achieves the milestone that seemed impossible 2 years earlier, one B-24 Liberator rolling off the assembly line every 63 minutes. 63 minutes from start to finish for a 4-engine bomber containing over 1.5 million individual parts. Assembled by workers who had never built aircraft before, Ford taught them systematic production methods. The 63-minute interval isn't arbitrary. It represents the theoretical minimum time required to complete all assembly operations if every process functions at optimal efficiency with zero wasted motion. Ford's engineers calculated this target by analyzing each individual task, measuring precise time requirements, and organizing workflow to eliminate every unnecessary step. Achieving this target required innovations that extended far beyond traditional manufacturing techniques. Materials flow through the factory on precisely timed conveyors that deliver components to each assembly station exactly when needed. Inventory sits neither too early, causing congestion, nor too late, causing delays. Everything arrives at the perfect moment for immediate use. Tool positioning receives similar attention. Every wrench, rivet gun, and measuring device has a designated location within arm's reach of the worker who uses it. No one walks across the factory floor to retrieve equipment. No time is wasted searching for misplaced items. Workers can focus entirely on their assigned tasks without distraction or delay. Quality control integrates into the assembly process rather than occurring as a separate inspection phase. Each worker verifies their own work using gauges and fixtures designed to detect problems immediately. Defects are corrected at the point of origin rather than discovered later when correction becomes expensive and time-consuming. The psychological pressure on workers is intense. Assembly line production tolerates no individual variation in timing or technique. Workers must maintain precise pace continuously throughout their shifts. Someone who works too slowly backs up the entire line. Someone who makes mistakes creates problems that disrupt dozens of subsequent operations. But Ford provides compensation that makes such pressure tolerable. Willow Run workers earn wages significantly higher than traditional manufacturing jobs. The facility operates 3 shifts daily, providing employment for over 40,000 people during peak production. Many workers are women entering industrial employment for the first time, earning financial independence that previous generations couldn't achieve. The social impact extends throughout southeastern Michigan. Entire communities spring up around Willow Run as workers relocate to take advantage of high-paying factory jobs. Housing developments, schools, and commercial districts emerge to serve the massive workforce. The facility becomes an economic engine that transforms the regional economy. Government officials who initially questioned Ford's unconventional approach now herald Willow Run as a model for wartime production. Secretary of War Henry Stimson visits the facility in April 1944 and declares it the most remarkable industrial achievement in American history. The assembly line that critics called impossible has become a symbol of American manufacturing superiority. But the true measure of success isn't production statistics or government praise. It's the impact on Allied combat operations in Europe and the Pacific. B-24 Liberators manufactured at Willow Run participate in every major bombing campaign from 1943 onward. They strike oil refineries in Romania, aircraft factories in Germany, submarine bases in France, and shipping in the Mediterranean. 8th Air Force records show B-24 groups flying from British bases completed over 150,000 combat sorties by war's end. 15th Air Force units operating from Italy flew another 70,000 missions. Pacific Theater B-24 seconds conducted thousands of long-range bombing missions against Japanese targets across vast ocean distances. Each mission required aircraft that functioned reliably under extreme conditions. Bombers operated at altitudes where temperatures dropped to 40 degrees below zero. They flew through anti-aircraft fire that could damage any system. They carried maximum fuel loads over distances that stressed every component. Mechanical failure meant death for 10-man crews operating hundreds of miles from friendly territory. Willow Run B-24 seconds proved as reliable as traditionally manufactured aircraft while being produced in quantities that traditional methods couldn't achieve. The systematic assembly process that critics predicted would compromise quality actually improved dependability by eliminating variations that hand construction introduced. Standardization meant that parts fit properly, systems functioned predictably, and maintenance procedures worked consistently. The strategic implications became clear by late 1944. Allied bomber forces could sustain operations that German industry couldn't counter. American factories were producing aircraft faster than the Luftwaffe could shoot them down. Every B-24 lost in combat was replaced by multiple new aircraft emerging from assembly lines that operated continuously. German aviation officials studying captured Allied aircraft expressed bewilderment at American production methods. Their intelligence reports described manufacturing techniques that seemed to contradict everything German engineers understood about aircraft construction. How could complex bombers be built using simplified procedures that required minimal worker training? The answer lay in systematic engineering that German industry, despite its technical sophistication, never fully embraced. German aircraft manufacturing retained traditional methods that emphasized individual craftsmanship and custom fitting. Each bomber was essentially unique, requiring specialized knowledge and lengthy assembly time. American mass production, exemplified by Willow Run, approached manufacturing as an engineering problem that systematic analysis could solve. Instead of relying on worker expertise, Ford designed processes that achieved superior results through mechanical precision and standardized procedures. The assembly line eliminated human variables that caused quality inconsistencies. By 1945, Willow Run had produced 8,685 B-24 Liberators, more heavy bombers than any other single facility in history. The 63-minute production interval, sustained over months of continuous operation, represented manufacturing efficiency that no other nation achieved during the war. But the achievement transcended mere production statistics. Willow Run demonstrated that American industry could apply systematic engineering to any manufacturing challenge, no matter how complex or unprecedented. The facility proved that mass production methods, properly implemented, could outperform traditional craftsmanship in both quantity and quality. The workers who built those bombers understood the significance of their achievement. Many had family members serving overseas who depended on Allied air superiority for survival. Every B-24 that rolled off the assembly line represented protection for American forces and increased pressure on enemy targets. The 63-minute interval wasn't just an industrial milestone, it was a weapon that helped win the war. Charles Sorensen later reflected that Willow Run represented the culmination of everything American manufacturing had learned since the Industrial Revolution began. The facility combined advanced materials handling, systematic workflow optimization, precision quality control, and human factors engineering into a coherent production system that achieved previously impossible results. The lessons extended far beyond aircraft manufacturing. Post-war American industry applied Willow Run techniques to countless products, from appliances to electronics to construction materials. The systematic approach to complex manufacturing that Ford pioneered became the foundation for American industrial dominance in the decades following World War II. August 15, 1945. The war ends with Japan's surrender, and the last B-24 Liberator rolls off the Willow Run assembly line after exactly 3 years and 5 months of continuous production. The massive factory that employed over 40,000 workers at peak operation begins shutting down assembly stations systematically, the same methodical approach that characterized every aspect of its operation. The final statistics tell a story that defies comprehension. 8,685 B-24 Liberators produced in 67 months, average production time, 63 minutes per aircraft. Total employment, over 100,000 workers throughout the facility's operation. Materials consumed, hundreds of thousands of tons of aluminum, steel, rubber, and specialized components sourced from suppliers across North America. But numbers alone cannot capture the revolution that Willow Run represented. The facility proved that American manufacturing could achieve production levels that seemed impossible, using methods that challenged fundamental assumptions about complex assembly work. Traditional aircraft manufacturers who insisted that bombers required individual craftsmanship and lengthy construction time were proven wrong by systematic engineering that approached manufacturing as a problem to be solved rather than an art to be practiced. The transformation of the workforce revealed something profound about human potential under proper organizational conditions. Workers who arrived with no aviation experience became specialized experts capable of building aircraft that met rigorous military specifications. The assembly line didn't dehumanize workers, as critics predicted. It provided them with skills, steady employment, and wages that enabled social mobility previously unavailable to most Americans. Many Willow Run workers remained in southeastern Michigan after the war, using their industrial experience to find employment in automobile manufacturing, appliance production, and other industries that adopted mass production methods. The systematic approach to complex assembly that they learned became standard practice throughout American manufacturing, contributing to post-war economic expansion that created unprecedented prosperity. The facility itself underwent conversion to automobile production, manufacturing cars using the same assembly line principles that had produced bombers. The building's enormous size and advanced materials handling systems proved equally effective for civilian products. Ford continued operating Willow Run for decades, producing millions of vehicles using techniques pioneered during wartime bomber production. Military historians studying World War II often focus on battles, campaigns, and strategic decisions that determined outcomes. But the war was ultimately decided by industrial capacity and the ability to produce weapons, equipment, and supplies faster than enemies could destroy them. Willow Run represented the apex of American manufacturing capability applied to military production. The strategic impact extended beyond the specific aircraft produced. Allied bomber forces that devastated German industry and Japanese targets relied on continuous replacement of aircraft lost in combat. Assembly line production meant that every bomber shot down could be replaced by multiple new aircraft, sustaining operations that traditional manufacturing methods couldn't support. German and Japanese aviation officials never achieved comparable production efficiency, despite possessing advanced engineering knowledge and skilled workforces. Their manufacturing remained rooted in traditional methods that emphasized individual craftsmanship over systematic optimization. Quality was high, but quantity remained limited by approaches that couldn't scale to meet wartime demands. The contrast illustrates a fundamental difference in industrial philosophy. Axis manufacturing focused on technical excellence achieved through specialized knowledge and custom fabrication. Allied manufacturing, exemplified by Willow Run, pursued technical excellence through systematic engineering that eliminated variables and standardized processes. Both approaches could produce high-quality aircraft, but only one could produce them in quantities sufficient to win a global war. Charles Sorensen's post-war writings emphasized that Willow Run's success resulted from treating manufacturing as an engineering discipline rather than a craft tradition. Every aspect of production, from materials flow to worker training to quality control, was analyzed systematically and optimized for efficiency. The assembly line represented applied science rather than industrial art. This systematic approach influenced American manufacturing for decades following the war. Industries that had never considered mass production methods began adopting assembly line techniques adapted from automotive and aircraft manufacturing. Electronics, appliances, construction materials, and countless other products benefited from systematic engineering that emphasized process optimization over individual craftsmanship. The social implications were equally significant. Mass production created employment opportunities for workers without specialized training, enabling economic mobility for millions of Americans. Assembly line jobs provided steady wages, health benefits, and retirement security that traditional craft employment rarely offered. Industrial work became a path to middle-class prosperity for families that had previously struggled with economic uncertainty. Labor unions initially resisted assembly line methods, viewing them as threats to skilled workers and traditional craft autonomy. But the high wages and steady employment that mass production provided eventually convinced most workers that systematic manufacturing served their interests better than traditional methods that offered individual satisfaction but limited economic security. Willow Run also demonstrated American industrial flexibility under crisis conditions. The facility progressed from empty land to full bomber production in less than 18 months, a timeline that traditional construction and equipment installation methods couldn't achieve. Emergency conditions revealed capabilities that peacetime manufacturing had never tested. This flexibility became crucial during the Cold War, when American industry needed to adapt quickly to new military requirements. The systematic engineering approach pioneered at facilities like Willow Run enabled rapid conversion between civilian and military production, providing strategic advantages that more rigid industrial systems couldn't match. International observers studying American manufacturing success often focused on technological advantages or natural resource abundance. But Willow Run demonstrated that organizational capability and systematic engineering were equally important factors. Other nations possessed comparable technology and adequate resources, but they lacked the systematic approach to complex manufacturing that American industry had developed. The legacy extends beyond manufacturing into management philosophy and organizational theory. Willow Run proved that complex problems yield to systematic analysis and that human performance improves under properly designed processes rather than through individual expertise alone. These insights influenced business practices, educational approaches, and government operations throughout the post-war era. Modern aircraft manufacturing still reflects lessons learned at Willow Run. Contemporary facilities produce commercial and military aircraft using assembly line principles adapted for current technology and materials. Computer-controlled systems handle materials movement and quality control, but the fundamental approach remains systematic optimization of manufacturing processes to achieve efficiency and consistency. The Boeing Commercial Airplane Facility in Everett, Washington, currently the world's largest building by volume, employs methods directly descended from Willow Run techniques. Wide-body aircraft move through assembly stations where specialized workers perform specific tasks using standardized procedures. The scale is larger and the technology more sophisticated, but the underlying philosophy remains unchanged. Military procurement continues to favor manufacturers who can demonstrate systematic production capability over those who rely on traditional craftsmanship methods. The ability to scale production rapidly during crisis conditions remains a critical strategic capability that systematic manufacturing provides better than individual expertise. The workers who built B-24 Liberators every 63 minutes at Willow Run accomplished something unprecedented in manufacturing history. They proved that American industrial capacity, properly organized and systematically engineered, could achieve production levels that no other nation could match. Their achievement helped win World War II and established manufacturing principles that continue shaping global industry. Henry Ford's obsession with efficiency, Charles Sorensen's systematic engineering, and 40,000 workers' dedication to precision created more than just bombers. They created a demonstration of industrial capability that defined American manufacturing superiority for generations. The 63-minute B-24 represented not just aircraft production, but proof that systematic thinking applied to complex problems could achieve results that seemed impossible. Every time a modern assembly line produces complex products quickly and efficiently, it reflects lessons learned at Willow Run. Every time systematic engineering solves manufacturing problems that traditional methods couldn't address, it demonstrates principles that civilian aircraft workers proved during World War II. The revolution that began with one man's conviction that bombers could be built like automobiles continues influencing how humanity approaches complex manufacturing challenges. The empty sky over Willow Run no longer sees B-24 Liberators emerging every 63 minutes. But the systematic approach to manufacturing that created those aircraft continues producing results that seemed impossible until someone proved that proper engineering could make the impossible routine. That legacy, measured not in aircraft produced but in problems solved and capabilities demonstrated, remains Willow Run's most significant contribution to human achievement under pressure. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.